In this video, I'm going to show you the process of building this advanced power bank. There are many DIY power bank builds online, but none of those have all the features that an engineer like me would like to have. So, I decided to design and build my own from scratch. Introducing the Omnibus 4x8. At its core is a 345 Wh lithium-ion battery pack. That's the equivalent of 96,000 mAh at 3.6 volts. The battery pack is arranged in a 4S8P configuration with the option of pushing up over 414 Wh using high-end cells. For this build, I'm using 3000 mAh cells, resulting in a 14.4V 24,000 mAh battery pack. An ESP32C3 module is the microcontroller that enables the input and output functions, monitors system parameters, and performs automated tasks. A 1.3-inch OLED display and a 3-way navigation button serve as the user interface, enabling you to access system features, adjust configuration parameters, and monitor telemetry data. The user experience has been designed to strike the perfect balance between simplicity and functionality. A short press on the right button wakes up the power bank, and there's an auto power off function to conserve energy. On the main screen, there's the quick access menu on the left side to control the core functions, and a telemetry display on the right side, which is selectable by long pressing the right button. A total of 8 ports are available on this power bank. On the right side, there's a set of 4 USB-C outputs rated at 36 watts each. Next to them are the bidirectional USB-C and the bidirectional DC ports, which can deliver 100 watts and 120 watts respectively. The XT60 port is connected to the internal 4S battery pack, capable of delivering over 400 watts of power both ways. Finally, there's the mains IC output with a capacity of 150 watts. The killer feature in this build is the bidirectional DC port. This port can take in or output 2.7 volts to 20 volts DC with up to 6 amps of current. In output mode, constant voltage and constant current regulations are available. This makes it suitable to power various DC power devices without the need for an AC power adapter, or powering up your electronic projects without the fear of short circuit. There are 2 modes available for the input mode: normal input and MPPT. In normal input mode, the power bank dynamically regulates the charging current within set values to prevent overloading the supply side. In MPPT mode, the power bank continuously tracks the maximum power point to achieve maximum power when used with a solar panel. The power bank has been designed with safety aspects in mind. A custom heatsink solution with multi-point temperature monitoring and active cooling mitigates any problems with thermal dissipation. The battery pack uses a proper BMS with its protection features, which is backed up with a discrete fuse for extra redundancy. All of these features are enclosed in the case with a form factor smaller than a sheet of A4 paper and the height of a AA battery. This makes the power bank fairly portable for its capacity and surpasses commercial solutions in terms of energy density by quite a margin. Enough for the introduction, let's start with the build process. To begin the design process, I gathered all the required components, in which I will explain the parts involved and the wiring as we go through the build process. All the resources for this project are available as an open source project. For now, let's start with the enclosure. This is the design I came up with for the Omnibus 4x8. The construction consists of solid plates, 3D printed side pieces, and metal spacers. This makes the entire build solid without relying too much on 3D printed parts. After finishing the enclosure design, I started printing all the necessary components. I used black ABS with these print settings. While those parts were printing, I printed 1:1 scale images of the top and bottom plate designs onto sheets of paper and cut out the outlines. I then glued the paper onto appropriately sized G10 fiberglass plates and began working my way through the guide templates. I started by rough cutting the outlines with a hacksaw, then moved to the bench grinder to refine the rounded corners. To ensure accuracy, I drilled pilot holes first, followed by a larger bit to reach the final diameter. Once the plates and 3D printed side pieces were ready, I inserted all the brass hardware into place and secured the structure together to complete the enclosure. To further refine the finish, I went through a progressive sanding process on the sides to blend the print lines and the fiberglass edges together. I then spray painted the 3D printed parts with a matte black paint. For ingress protection, I added metal meshes to the fence on the 3D printed side pieces. The enclosure was finally complete. For the battery pack, I bought 32 brand new 18650 cells. Upon arrival, I tested their voltage, internal resistance, and discharge capacity. Once I confirmed everything was well within spec, I began the process of assembling the battery module. I first mounted the 3D printed bracket onto the bottom plate, then slid the 18650 cells into the bracket and fixed them in place with a bit of CA glue. I repeated the process for the second half until I had 2 completed battery modules. To wire up the battery pack, I used 8 by 0.2mm nickel strips, 14 gauge silicon wires, and a 4S30A BMS board. Here's the wiring diagram for the battery pack. I began spot welding the strips to form a 2S8P configuration on each module. I then applied battery covers to the adjacent sides of the battery modules for insulation. Once the battery modules were ready, I mounted the left module to the bottom plate, installed the BMS board, and soldered the 14 gauge wire like this. I then made all the necessary connections for the balance port before mounting the right battery module into place. With that, the battery pack was finally complete. The high current circuit is handled by a custom power distribution board based on this perf board featuring these specific modifications. I mounted the components to the board as shown before tinning the traces with an adequate amount of solder. The finished board should look like this with the copper bus, the fuse, and the current sense resistors all properly soldered. The power distribution board is mounted to the bottom plate with a set of M2 screws. I then soldered the positive LED from the battery to the input side of the fuse and connected the negative side of the power distribution board to the negative output of the BMS board. For the controller board, I fabricated a custom platform out of another perf board and mounted it in place with M2 spacers. The final setup should look like this. To create the custom heatsinks, I used a 2mm aluminum plate and the 3D printed templates as a guide. After gluing the templates down, I drilled the mounting holes and rough cut the profiles using a hacksaw. I refined the shape using a bench grinder for the exterior edges and a hand file for the internal cutouts, resulting in a set of custom fitted heatsink plates. To thermally couple the power modules to the heatsinks, I used a 0.5mm thermal pad. I applied the pad to each heatsink plate and trimmed the excess with a surgical knife. To fix the power modules in place, I used a set of M2 nylon screws. I pierced the holes on the thermal pad for the screws to go through and inserted all of the screws into their place. I continued the process by mounting the IP2368 module onto the heatsink, followed by all 4 XPM52C modules. Before mounting the SC8TX12A module, I removed its onboard microcontroller, trimmed the capacitor legs, and then mounted the SC8TX12A module onto the heatsink. With everything in place, I installed the M2 brass spacers and began the final integration. The completed heatsink assembly should look like this. After the power modules were in place, I began wiring them up. Here's the wiring diagram for the power modules. I first soldered the wires to the MOSFET and secured it to the bottom heatsink with a bit of thermal glue. I then soldered the drain of the MOSFET to the negative side of the XPM52C modules and the source to ground. For the SC8TX12A module, I soldered the power connections directly to the SMD capacitor. Here's the complete wiring for the lower assembly. For the top assembly, I completed the wiring for the remaining XPM52C modules. I soldered the power connections for the IP2368 module to the leads of the capacitor as well. I finished it off by soldering the rest of the connections to the power distribution board. The finished wiring should look like this. In this part, I began the process of assembling the display panel. Here's the schematic for this section. I used a piece of perf board cut to the specific shape and soldered the tactile switches in this layout. I then mounted the board to the 3D printed panel and soldered the remaining components. The finished display panel should look like this. I continued the process by assembling the control board. Here's the schematic for this section. To power the circuit, I used this buck converter with the potentiometer and pull-up resistor removed and the output voltage set to 5 volts. I then soldered the buck converter, the ESP32, and the display panel connector to the perf board like this. Before installing the INA219 sensor, I removed these resistors on the board, then trimmed the PCB to reduce its form factor. I soldered the remaining components to the control board until it was partially assembled like this. I finished it off by installing the control board to the power bank. I uploaded a test code and powered the system with a bench power supply first. Everything seemed to work well, but the standby current was a bit high at nearly 1 mA. I decided to optimize the circuit, but this is when I accidentally damaged the ESP32 and the SC8TX12A module, so I had to progress without the module for a while. I further improved the circuit and the layout for the control board, which ended up looking like this. I then measured the standby current once again, which has dropped to just under 400 microamps. I checked the USB output functionality, which appeared to work fine. I then plugged the power bank into a power source and checked the power readings to confirm the sensor was working properly. For the mains output, I used an off-the-shelf inverter unit. I removed the inverter module from its case. I like this particular one because the power components are thermally coupled to the PCB rather than the case. This should make the build process easier since I don't have to design custom heat sinking, but that's where the convenience ends. Like most inverter units, this one operates within a specific voltage range. According to the manual, it takes 9.5 volts to 14.5 volts DC, which is lower than the voltage of a fully charged 4S lithium-ion battery. I could have used a buck converter for pre-regulation like many other projects, but since space and efficiency are at a premium, I decided to modify the inverter module itself to safely handle the higher voltage instead. For this modification, I had to verify the components on the inverter module. First is the input capacitor, which must be rated higher than the peak operating voltage. I checked the push-pull MOSFETs and confirmed they can handle the higher voltage. I also ensured the PWM controller can handle the full 4S lithium-ion battery voltage. All of these components were safe, which left me with the transformer. This transformer was wound for a 12 volts input and needed to be rewound to safely run at the higher voltage. I placed a single turn to the core, which measured a peak voltage of 3 volts. This means the transformer was wound at 3 volts per turn and there should be 4 primary turns in each direction. For the modification, I decided to increase the primary winding to 5 turns. I began removing the transformer by hitting all of the pins simultaneously until the transformer fell out on its own. I continued the disassembly process until the core was separated. On the first layer, I was greeted with the first half of the secondary winding. I carefully unwound this layer as I'll need to put it back on later. With the first half of the secondary out of the way, I had access to the primary. I removed the original primary winding and prepared the wires for the new winding. I wound 5 turns for the first half of the primary, followed by the second half. Finally, I rewound the secondary back onto the core and reassembled the transformer. I soldered the modified transformer back in place. I ran the SAM test again and now it shows a lower peak voltage of 2.4 volts. This indicates that the modification was successful and the transformer can now handle the higher input voltage safely. The under voltage and over voltage protection is controlled by the PWM controller chip. I checked the range and found the protection triggered at 10.5 volts and 15.6 volts. To shift this range, I had to modify the voltage divider responsible for the voltage sensing. By adding a 22K resistor in parallel with the lower resistor, I shifted the voltage range higher so the inverter can now run at a higher voltage. To control the inverter, I utilized the unused power switch connection. I first removed the components for the USB output and the jumper for the power switch. I then soldered the main power wires and the power signal wire. After mounting the inverter board, I set up a drive circuit on the control board to enable the inverter with the ESP32. I finally checked the AC output to confirm everything was working properly. I implemented multi-point temperature monitoring with 4 DS18B20 sensors. I soldered the wires to each sensor and then applied them to the critical areas. First to the battery pack, second to the top heatsink, third to the bottom heatsink, and fourth to the inverter module. I soldered all of the sensors to a single bus and checked the temperature readings to make sure the system was working properly. For the active cooling, I integrated a pair of 40mm fans. I secured the fans to the 3D printed side piece and soldered an extension wire to the fans. Once the fan assembly was ready, I installed it into the power bank. I set up the drive circuit to control the fan and soldered the fan wire to the control board. A spin test confirmed the cooling system was working, completing the thermal management system. After I received the replacement chip for the ST8812A module, I replaced the damaged chip with a new one. I made sure the module worked in a standalone setup before installing it into the power bank. I soldered the DC jack to the output capacitor of the module. The entire wiring at this point should look like this. For the battery interface, I soldered 14 gauge wires to the power distribution board and an XT60 female connector on the other end. Now that the wiring was done, I mounted the control board and temporarily assembled the power bank to test all of its functions. With everything working as intended, I began the final assembly of the enclosure. I installed the 3D printed side pieces to the bottom plate and the display panel to the top plate. After installing the remaining screws, the Omnibus 4x8 was finally finished. We've come a long way since the start of this build. Ever since my original guide in 2018, I've had a vision of what my next power bank should be. I feel confident in every decision made throughout this project, tackling every problem from an engineer's perspective to ensure the most elegant solutions. I truly believe this pushes the limits of what's possible with off-the-shelf modules, though a fully custom design is the next logical step in the future. Thank you for watching, and I will see you next time.